can try with mine.
Okay.
Is it better now if I speak like this?
Yeah.
Hello.
Okay.
Is it better now if I speak like this?
Okay.
Perfect.
So maybe you have to restart.
I restart? No problem. So from the beginning here?
Yeah, no, maybe
yeah. Okay. So as I said, we are considering conservation laws in this presentation, and in particular one-dimensional scalar conservation laws. So we consider the scalar case because for two reasons. First, it will be easier within the presentation, and second, the last result that I will present will be only proof for now for scalar conservation laws, though we hope to prove it for systems of conservation laws. So even for now, every result will be applied only for scalar conservation laws, and you can't apply them at least until further notice for more general systems of conservation laws. So a general known fact on this type of PDE is the fact that you can observe discontinuities that can appear after finite times. So for instance, if you consider the Burger's equation with this initial condition, you can solve, at least for some time, this PDE using the method of characteristics. It will tell you that essentially this part of the solution will be transported at speed 1, this at speed 0.5, this 0. Essentially, you're transported at the speed equal to your value. So if you compute the solution, after some time, you will see a discontinuity that appears. So it's a fairly common fact for this kind of PDE, and it creates a lot of issues both on the theoretical and numerical side. And today we focus on a numerical issue, which is for finite difference schemes. Are we able to capture those discontinuities? It's a difficult fact because finite difference schemes are essentially obtained by Taylor expanding the derivatives that appear in your PDE. And so you assume some kind of regularity to have a finite difference scheme that is consistent with your scheme. But the question is what happens when there are discontinuities. So since this is a very difficult question, we focus on an even simpler question, which is, can you approach shocks? So just to recall what a shock is, it is a solution that is composed of jump between two constant states, so u minus on the left and u plus on the right, and that travels at speed s. So this is what you see on the function u. And you know that this is a weak solution of your conservation law if it satisfies the Rankine-Hugoniot condition. So this first condition that is present. Most of the time, you need to add some additional hypothesis, entropy hypothesis on this solution to be the physically relevant one. Here we introduce the lax shock condition. If you think about it, this lax shock condition is essentially saying that the characteristics are entering the shock a little bit like we saw before. Essentially, you're traveling towards the shock. So those shocks are weak shocks and they are known as lax shocks. And in this presentation, sorry, I have a quick thesis, I will consider steady lax shocks. So essentially, I will consider steady solutions that are a jump between two states, which will be weak solutions of our conservation. So now, as I said, we have introduced our PDE and the solution that we're interested in. So we need to introduce our finite difference schemes. So there is a lot of things on this slide, but don't worry, there is not a lot of things to remember. The only thing that you need to remember is this rectangle in the middle, essentially. I will just try to present overall what's happening. You introduce a Cartesian grid for your space and time, so with a space step delta x and a time step delta t, and the goal is to find values at each node of your grid, so that essentially the value on at the point should be approximately equal to a good approximation of the solution, at least on some cell, which is defined here, which is a cell of size delta t and of size delta x in space and in time. The question is, how do you compute those values u and j? And to do so, you will need to introduce a finite difference scheme. So this is essentially this formula here that says that un plus 1 is n of un. This operator n is known as the discrete evolution operator. it's the operator that allows you to compute the values at the next time step using the values at the time step n. For a conservative finite difference scheme, this operator n has the following expression, where you can see some discrete derivative, discrete version of the derivative that appears in your conservation law. So there are a lot of things that are parameters that appear here. You don't need to remember all of them. I just want to point out some things. The first is that this function f is known as a numerical flux. It should be some approximation in some sense of the flux that appeared in your conservation law. We will see in the next slide what we need to assume on this f to be consistent with your initial PDE. The second thing is that there are two integers p and q that appear here, which essentially defines the stencil of your numerical scheme, which means how far you need to reach to get your information, how much you need, how much points you need. For this presentation, we won't make any assumption on those integers, which allows us to consider difficult schemes, high-order schemes, for instance. Finally, we introduce a new, which is the ratio between the time step and the space step. And for this presentation, this ratio will be considered to be fixed. Now, the only thing that you really need to remember is that this operator n is essentially the operator that allows you to compute the next time step. Now, most of the time, you need to introduce some usual assumptions on this kind of numerical scheme. So the usual ones are a consistency condition that links your numerical flux and the flux of your conservation law, some CFL condition, some linear stability near constant states. Those are usual conditions. And then we will introduce within this presentation an additional hypothesis, which is a diffusion assumption. Essentially, we assume that the scheme will introduce numerical viscosity. I won't go into what I mean by that in depth, but you will. This is an assumption that will essentially discard the Lax-Ventrov schemes, for example, which are dispersive schemes. For the presentation, I will only consider first-order schemes for the different estimates that will appear, because it will be easier. Now that we have introduced all of this, I just want to point out that there will be an example that will follow us throughout the presentation for numerical representations and so on. So I will consider the Burger's equation. I will consider the shock 1 minus 1. And for the numerical scheme, I will consider the modified Lax-Friedrich scheme that is defined at the end of this slide. Now, let's enter in the real content of this presentation. What is a discrete shock profile? A discrete shock profile is essentially a solution of your numerical scheme, which is a traveling wave. This is what this line tells you. You see a difference between the space parameter minus some speed times the time parameter. So it's a traveling wave which must link the two end states u plus and u minus. So essentially, it's some kind of equivalent of your shock for the numerical scheme. Now, I've put here the definition. However, there are a lot of remarks to be brought towards this definition, which is actually far more complicated than it seems. However, for this presentation, as I said, we will focus on steady Lax shocks. So the definition is actually much simpler. A stationary discrete shock profile is just a fixed point of your numerical scheme, a fixed solution, a stationary solution, which links the two end states of your shock. So what does it look like? If I consider the example that I introduced the slide before, so the shock 1 minus 1 for the Burger's equation with a modified Lax-Friedrich scheme, I introduce the usual initial condition for my numerical scheme. So I take the mean on each cell of my shock, of my initial condition, which is a shock. So you will have 1 on the left, 0 on the middle, because you have half of the cell that is equal to 1, half of the cell that is equal to minus 1, and minus 1 on the right. And now I will apply my modified Lax-Friedrich scheme. After some iterations, I seem to converge towards some stationary solution of my numerical scheme. Also, this stationary solution seems to connect the two states 1 and -1. This is a stationary discrete shock profile. So there are a lot of things to say already here. First, because we are considering a diffusive scheme, we see that there is some kind of viscous behavior that appears, some parabolic behavior. If I were to consider, for instance, the Lax-Venvorth scheme, which is a dispersive scheme, I will see rather dispersive behavior appear. So, for instance, oscillations near the shock. The second thing that is interesting to point out is the fact that here there are essentially an exponential convergence of my discrete shock profile towards its end state. And this means that to pass from the state U minus to the state U plus, I essentially have a transition that is contained in a finite number of cells. Now, if you remember, each cell is essentially of size delta x, meaning that this transition on the real space and time is essentially contained in a zone of size big O of delta x. And if you take delta x going towards 0, essentially you are approximating your shocks pretty well. So this is why this kind of solution is actually, this kind of object is observed, and essentially we hope to observe them. It creates some kind of heuristics that one would want to follow, which is that if you want a finite difference scheme to be able to capture discontinuities, you need to essentially prove that for each stable shock wave, each entropic solution, entropic shock wave of your conservation laws, you would want to have some stable discrete shock profile. This creates two fields of research. The first one is the existence of those discrete shock profiles, and the second one is the stability of them. So I will talk about the second one, but let's talk a little bit about existence. Existence is actually a little bit more precise than what I said before. There does not exist on one discrete shock profile, but actually you can prove that there exists, at least for lax shocks, a continuous one-parameter family. So there are some results that exist by Jennings, Majdarazan, and Michelson. So here in blue you had the discrete shock profiles that I introduced before, and in red you have a family of continuous stationary discrete shock profiles. All of them are obtained essentially in the same way as I obtained before. So you don't have only one discrete profile.
Sometimes it is clear because since it is invariant by translation, any translation of this problem is a solution.
Yes and no. It's trivial and not trivial because you don't have a profile, a whole profile on R that satisfies the properties. What you some results prove this, but you can't. You do not. The general theory does not allow to say I have a profile U here. If you consider, for instance, this definition here, this U bar is only defined on Z plus some speed times Z. So it's not defined on R, and then you can say each translation is a discrete shock profile. Sometimes it's only defined on some neighborhood of this set. And so you can't say that it's translation in some ways, but I think it's a bit more difficult to. It's in the continuous setting. Most of the time, you say, okay, I have one traveling wave. Each translation is a solution. In this case, it's a little bit more peculiar because it's not necessarily. You don't have necessarily a profile.
Yeah, maybe you are not passing from the same nodes because if you translate a different quantity, then just the space step, you are not on the grid.
Exactly. That's it. This works only for translation. This definition works for translation which are S new. So here it's you need to translate from entire cells. But here I'm saying you can translate essentially from it's a way to say it, I guess. So it's a bit more peculiar. One thing that I will add is the fact that I will, for the rest of the presentation, I will consider one of the discrete shock profile as being a little bit more special. It will be clear afterwards. And I write it in blue, and it will be defined as U0. An assumption that you can also be made, which is pretty much a fact in the context that we present, okay, is the fact that the mass function that is defined at the bottom of the slide must be injective. This mass function is essentially the sum of the differences between the blue and the red solution. So it's the mass of the mass of the difference between the two discrete shock profiles. I will explain why this is important just afterwards, but as you can see here, I put the M delta at the top, and you see that essentially it seems to grow linearly, so you can hope that it is true. Now, let's talk about stability, which is the main subject of the presentation. What is nonlinear orbital stability? The goal is to find two vector spaces, x and y, such that if you take an initial perturbation h that must be small in x, then if you consider the solution which is equal to your reference discrete shock profile plus this small perturbation, if you consider the solution that is associated, it must tend to be close to the set of all discrete shock profile in the y norm. So to give some visual representation of what it means, here in blue you have your discrete shock profile that is hidden behind the red curve, and in red you have the discrete shock profile plus some perturbation that I put far from the shock here. I apply my numerical scheme, and what appears is that the perturbation seems to go towards the shock and then translate it. So it's kind of related. But essentially what we see here is the fact that we tend to get close to the set of discrete shock profiles. And even more, it seems as if we converge towards one specific discrete shock profile. It's even stronger to some extent than what is presented here. It would be more that there exists some delta such that this tends towards 0. The question is, who is delta? Who is this discrete shock profile? I claim that there is a way to determine this using the conservative properties of your numerical schemes. Essentially, through time, the sum of the differences between the red and the blue curves are conserved. So this is what is said here. So the sum of the differences here are the same as the beginning. And if you suppose that your solution converges towards some discrete shock profiles in L1, let's say, then necessarily going to the limit in the bottom in this equality, you have that the mass function determines what discrete shock profile you're converging to. So essentially, the mass of your initial perturbation tells you I must converge toward this discrete shock profile. As a consequence, if I consider a zero mass perturbation, I should converge back towards the initial discrete shock profile. This is what appears. So this is just a general presentation of what nonlinear orbital stability is. Now let's talk about some state of the art. I will present 4 results which represent, in my opinion, the overall the overall results that exist in this field. And I will kind of present where there are limitations. So the first thing is that some results are limited to the case of scalar conservation laws, and it's strictly limited. For example, the result by Genix uses monotone schemes, so you need to work in a scalar case. So it only works for scalar conservation laws, which is good, but hopefully you would want something that works for systems. In the results that work for systems, there is one recurring limitation, which is that it only works for weak lax shocks. Weakness means that the amplitude of the shock must be small. The two states must be fairly close. Third limitation is the fact that some results are limited to specific schemes. So, for instance, monotone schemes, the Lax-Venner scheme or the Lax-Friedrich scheme, and you would want something that works for something more general. And finally, there are limitations on the choices of initial perturbations. So either by putting assumptions that they must be small in some exponentially weighted LP space, or that they must satisfy our polynomial weights, for instance, or that they must satisfy some zero mass assumption. As we saw earlier, it's sometimes something that is quite interesting because you converge back towards the initial discrete shock profile. So the main goal would be to prove a result that works for systems of conservation laws, that would apply for a fairly large family of numerical schemes, that introduces the fewest amount of restrictions on the perturbations. And finally, and maybe this is the most important, if it works for system of conservation laws, we would want to avoid introducing any weakness assumption. So the goal that was kind of set by Denis in 2007 in a review of discrete profile was to remove this weakness assumption and replace it by some spectral stability assumption on the discrete profile. So I will describe what discrete spectral stability is just after, but it essentially amounts to saying that you want additional information, additional restriction on the point spectrum of your discrete profile. Now, to do this, the idea that was proposed is to adapt techniques à la Zumbrunn. When we say à la Zumbrunn, it's because it's a recurring offer on the papers, but with, for instance, Peter Howard or Corrado Macia. And those ideas are applied to study the stability of traveling waves for parabolic PDEs.
So when you say weakness assumption, you mean smallness? So
yeah, the smallness assumption.
So the initial mass of the perturbation, something like that, no?
No. On the smallness assumption is on the size of the shock. The two states, U minus and U plus, must be close in most results. We would want something that works for strong shocks. And so the idea would follow fairly usual heuristics. You would want to have spectral stability, imply linear stability, meaning some decay of some semigroup or some family of linear operators, and then obtain some nonlinear stability using, for instance, Duhamel's formula. So the rest of the presentation will be separated in those two. The rest of the presentation will be essentially proving each of those two steps. So first, how do you go from spectral stability to linear stability? This part of the presentation is we present the content of a paper that I introduced, that I deposed on arXiv last year, but is an extension of results that were proved by Pauline Lafitte and Denis in 2003 and 2007. So just to give a quick overview, as I said, it's based on works by Zumbrunn, Howard, and Macia. And the idea is that you will have some spectral information on your linear operator, which you want to translate into estimates on the semigroup. The problem is that, as will be clear afterwards, there is no spectral gap, and there is an eigenvalues of modulus 1 that lies inside of the essential spectrum. Those are two real difficulties for the analysis, and the solution that was obtained by Zumbrunn, Howard, and Macia is essentially to rather than study the semigroup of the operator, you will study its Green's function. So I need to introduce the linearization about discrete profiles. First, when you linearize an operator near the constant states, you obtain operators of the following form here. Those are convolution operators. So you can easily define their spectrum using Fourier theory. Essentially, using the assumptions we introduced on the numerical scheme earlier, those spectrums will be curves of essential spectrum where one will belong to this and the rest of the spectrum must be inside of the unique board. So you have some dissipativity that appears here. Now, a little bit more complicated is how do you define the, can you say on the linear operator, which is the linearization near the discrete profile? This is much more complicated because the definition of this linearization has some spectral dependency on the coefficients AJK that appear here. Because this time they're expressed using the derivatives of your numerical flux about the values of your discrete profile. An important fact is that those coefficients converge towards AK plus and AK minus at infinity, because if you look at those coefficients, if you consider that J converges towards plus or minus infinity, they converge back towards the derivative near the end state. So because those coefficients AJK converge towards AK plus and AK minus, this means that at infinity, your linear operator acts like the convolution operators L plus and L minus. This will allow you to obtain spectral information on this operator. So I'm just recapitulating the information that is known. The first two things that the linear operators, the spectrum of L plus and L minus will belong to the spectrum of the operator L. Second point is that outside of those curves of essential spectrum, there will only be point spectrum, meaning that there will only be eigenvalues. And the last thing is that 1 will be an eigenvalue of the operator. So coming back to the comment of Roberto, since you can, essentially the way you can think about it is that since translate if you were to think in continuous settings, this is equivalent to invariance by translation. Essentially, the derivative of the discrete shock profiles is in a fixed point of the linearization because of this equality. This is just formal. Now, what is spectral stability? This is adding more information here. The first thing is that, as we saw, 1 is an eigenvalue, but we want it to be we want more information, more precisely. We would want that events function. Sorry, I need to read what the events function is. The events function is essentially an equivalent of the characteristic polynomial for your operator L, meaning that it's a holomorphic function that vanishes at values which are eigenvalues of your operator. This means that because 1 is an eigenvalue, your events function will vanish at 1. Your assumption is that 1 will actually be a simple zero of the events function. This is very theoretical, but more concretely, this will tell you that 1 must be a simple eigenvalue of the operator. Now, the other hypothesis that you need to introduce is that there are no other eigenvalues of modulus equal or larger than 1. Any right points here must be strictly inside of the unit circle, unit ball. Now, what's the Green's function? The Green's function is applying your semigroup to an initial data, which is a direct mass. So here, I will represent the behavior of the Green's function for the example that I introduced before. Here you have a direct mass at J0 equal to 30, at some place, J0 equal to 30. And I will apply the linearization of the modified explicit scheme about the discrete shock profile. We see some kind of behavior. It seems like the direct mass is translated along the characteristics of the right state towards the shock. And when it reaches 0, which is the shock position, it activates some profile, which seems stationary, meaning that it should be the eigenvector associated to the eigenvalue 1. The main theorem that I prove is essentially what I just told you, but in a more concrete analytical way. So essentially, you need to to present the behavior of the Green's function in three different parts that I represented here. This red part is a Gaussian wave that starts at J0 and is advected along the characteristics of the right state towards the shock, because you have a lax shock. When it reaches, on the left side, sorry, you have this green term, which is essentially nothing. It's just an exponential profile that gets activated and then decays back towards 0. And this term here corresponds to the activation of the fixed point. So V here is a fixed point of the operator L. And this function E is a function that goes from 0 to 1, meaning that in time you activate this eigenvalue. So this is essentially what we saw before. You're just translated and then you activate using this function. An important fact is that this description is uniform in J0. This is what you see here. So you have a similar description on the left. And also another important fact is that the result is actually a bit more stronger than what I presented. You actually extract the main behavior of the Green's function, and you also prove similar results for the discrete derivative of the Green's function. And also it works for here I presented the result for the first order schemes, but it works for higher order schemes. And more importantly, this works for systems of conservation laws. However, the result is far more difficult because you have more waves that appear. Essentially, when a traveling wave reaches the shock and activates the eigenvalue, you have also reflected and transmitted waves that appear. So the formula is far larger and far more difficult to handle. Just to give a really quick impression of how the proof works, essentially you need to express your Green's function using the inverse Laplace transform. You have this formula that is at the top, where you have some path that must surround the spectrum of your operator, and some function here, which is known as the spatial Green's function, which is the resolvent of the operator applied to a direct mass. You need two things. You need to meromorphically extend this function near 1 so that you can go through the spectrum, which is not evident because you have the resolvent that appears here. And then you need to find a suitable path gamma. I won't explain how you do this. But now that you have this description of the Green's functions that I introduced before, I claim that you have some linear stability because if you have this description of the Green's function, because you have this expression of the semigroup, which is essentially saying that you have a convolution product between your H and the Green's function. Using this description, you can actually prove decay estimates on your semigroup. This is essentially proving that this Green's function was the right thing to study. Now, to finish, I will present just quickly the results on the nonlinear orbital stability. So, with regards to this, I will just recall what I introduced a little bit earlier. So if I consider an initial perturbation in L1, let's say, and that there exists some delta such that this equality here, m delta is equal to the mass of the initial perturbation is verified, what I hope for is that the solution of my numerical scheme initialized by the discrete shock profile plus my initial perturbation should converge back towards the discrete shock profile associated to the delta that is defined by this equality. So what I want is to prove estimates in some suitable norm on this Hn, which is Un, the solution of my numerical scheme, minus the n discrete shock profiles that I hope to converge towards. I claim that the right spaces to do so are polynomial, at least using the techniques that were applied in my paper, are polynomially weighted norms. So essentially, you need to introduce this space of sequences such that this sequence 1 plus j to the power gamma hj must be in LR. So the gamma will be at the bottom here. We describe the power of the polynomial power that will added to that will be introduced on the sequences H. So using this, the nth nonlinear stability theorem that we obtain is the following one. So there is quite a lot of things to say but I will kind of shorten it a bit. We introduce a constant P. This constant will appear at the end and will correspond to a decay rate that you want to obtain. You want to obtain some decay rates on the Hn. This constant P will correspond to what you want to obtain. I claim that there exist two constants Upsilon and C, such that the perturbation must be in some polynomially weighted space and must be small in it. So the initial perturbation must be small in some polynomial L1 space. If it's the case, you can prove first that the identification relation here saying that the mass of your initial perturbation is equal to m delta will be verified for some delta. And the second thing is that actually you can prove decay estimates on the sequences Hn at the rate 1 over np and 1 over np plus 1 over 2, depending on whether you're looking in the L1 in a polynomially L1 space or a polynomially L infinity space, polynomially weighted, sorry. So two important things to point out. first, this only used spectral stability, so we didn't need to introduce any weakness assumption, as we said on the shock. An additional fact that wasn't in the previous papers is also that we have explicit decay rates that appear here for the sequences HN, which was not obtained before. Those decay rates seem to be fairly sharp. I would put emphasis on the seem to be, because I'm not sure if my numerical method is the best one to judge of this, but at least it seemed to prove that actually the slopes that we obtain are close to the slopes that are expected via my theorem, both in the L1 norm and the L infinity norm. Now I will talk very, very briefly on how the proof works. It's essentially what I said before. It will use some Duhamel formula. Essentially, you will start from your initial formula for your numerical scheme. UN plus 1 is equal to NUN. And you separate the linear part and the remainders, which are here quadratic remainders here. Now, this tells you that you obtain this equation 2, which is L delta. L delta is a linearization about the discrete shock profile U delta plus identity minus T applied to the quadratic remainder. And using the Duhamel's formula, you obtain some formula for HM depending on the HM for M between 0 and n minus 1. This allows you, using a recursive proof, to obtain some to estimate. However, there is a catch. We can't obtain anything here because we don't know any estimates on these families of operators here. We assume spectral stability near U bar, but not near U bar delta, not near every discrete shock profile, only near the initial one. So this does not allow us to conclude. We need to introduce something more, and essentially we will, rather than taking L delta here, we will choose L. So this create and put the L delta here in some source term, and this creates a little bit more of a difficult family formula, with this time 3 terms, but this gives us something where we can 3 families of operators on which we need to obtain decay estimates. We use the Green's function to obtain decay estimates on those families of operators, and this will allow us to obtain the theorems that I presented before. So I hope it wasn't too quick for the proof, but I think that this allows me to conclude. So just to recapitulate, to summarize, the first theorem on the Green's function is proved for systems and is essentially proved also for a large family of schemes. However, the second proof on the nonlinear stability theorem is not proved for systems of conservation nodes, but is something that I think should be doable with a little bit more careful analysis. And there are several other perspectives. You can look at moving shocks, you can look at overcompressive, undercompressive shocks, you can look at dispersive schemes. Essentially, this is a first step, I think, towards generalizing this theory for a much more wider set of schemes and of shocks. And also there are subsequent questions which are related to multi-dimensional cases. For instance, there is this known carbuncle phenomenon, which essentially is an instability of shocks, or at least of approximation of shocks. And this could be explained using instabilities of discrete shock profiles, essentially. So I hope that it was interesting, and thank you for your attention. If you have any question,
so thank you very much. Maybe we have questions. Anyway, first of all, clearly you are not using for the linear part. You are not using the monotonicity of this calculus.
No.
So I didn't catch for the nonlinear part. Mm-hmm. What are you using really? I mean, why it is not possible to do at the moment with the system case?
It's not that it's not possible. Okay, there are a few difficulties. First, as I said, in the system case, there are additional waves that appear. The main difference is the fact that you have waves that are going to infinity, meaning that all the mass is not concentrated at the shock. You have mass that goes to infinity, meaning that you need to adapt your norms depending on the mass that is going to infinity. So you need to essentially find projections, adapt your norms to take into account that a part of the mass will be centered here, but there is also a part of the mass that is going away. I don't think it's difficult. I think that it needs some thinking. That's the first thing. The second thing that is a bit more difficult, that creates difficulties, is that I think that there are questions surrounding this mass function here. So this mass function, in the scalar case, essentially, if I take any perturbation, I can find an associated discrete profile because it's a scalar. So if I sum this, if I take any perturbation, there will be some delta such that this is true if it's small enough. In the system case, since it's vector valued, it's not that clear. And essentially, you need to think about, okay, also the initial perturbation, there is some part that will be related to this, to choosing which discrete profile I'm converging to. But the rest, what do I do with it? And I think that it's also related to this question of what goes to plus and minus infinity. So it's a little bit more complicated, and it would require adapting the proof to it. I don't think that there is any big roadblock that comes to mind for now. Though I'm starting to think lately that maybe you can't do it. You can't do like this. You can't do this trick here where you introduce L delta and then say L delta minus L to kind of come back to the initial. I think that you will need to only consider zero mass perturbation, maybe. I'm not sure. I still haven't really put a lot of work into this because I just finished this paper. But I think that this is, I don't think that there is any big roadblock, but I think it needs some work.
Because for system, what I expect, the fact that if you want to prove stability, okay? So you need to find a suitable, functional, which is in some sense contracting. In the scalar case, you have monotonicity, so you have contraction L1. Here, for systems, usually it's much more complicated because you have no contraction L1. So, to take into account the fact that the quadratic perturbation is stable, usually you have to deal with more subtle remarks like the Bressan operators and so on. Usually when you have this kind of near a shock, you have some interaction operator, gleam operator entering the framework. Which is adapted to have some decay, and so to control the perturbation.
So I can see that, but I think that it's not even so. You're thinking about trying to find this function that goes towards zero. I think that it's true that, for instance, in L1 you don't have contraction, but for instance in L infinity, those waves going to infinity don't pose any problem because they're going towards zero in L infinity norm. Yeah. So what I was thinking is that you could look into some norm that towards when you project them along the outgoing, let's say characteristics. I don't know, depending on outgoing characteristics, you should choose L infinity norm, and then going towards the shock profile, which is actually you can prove that it's linearly independent from the rest. You will take the norm that I introduced before. I don't know if it's clear, but I think that it would allow you to prove something. I'm not sure, but I think it's something to follow.
Yeah, maybe it's not clear because when you have two shocks, usually it's the real matter that you have the symmetric energy, and so the outgoing shocks from the interaction, because here you have a perturbation maybe generating some shocks, intermediate shocks, which you have to control anyway. Because you have not just a simple perturbation. if you have no restriction on the kind of perturbation, you have perturbation generating new shocks, for instance.
Yes, of course. Yeah.
So you have shock interaction to take into account. But morally, people think that this kind of interaction is controlled by the fact that anyway you are dissipating something in each direction. So finally you have a stability.
Okay.
But if you have, so you need a function to control this kind of interaction.
Okay.
And so I'm not sure that your norm is enough to control this interaction all the time.
Maybe not. I need to. I'm still thinking that it will work. It's my opinion. I don't know if it's. I don't know if I understand, because what you're saying is that you could introduce initial perturbations that would kind of make you lose everything. But I think that this smallness assumption kind of restricts things, your choices of initial perturbations really strongly, because it's like you don't choose like L infinity perturbations, which would be.
You have a small L1 perturbation with a very big bounded variation. It's not impossible. In this case, you have small shocks interacting wildly, but then dissipating. So in some sense, I'm sure it works. But to take into account this dissipation, you need a more elaborated function.
Okay.
Otherwise, we have no way to control these shocks. I mean, in the monotone case, since you have monotonicity, you stay bounded between two perturbations.
Yes.
Here, there's no reason you can have oscillations, once oscillation, because there is no monotonicity.
True, but like
constraint on the perturbation.
Okay, I see what you mean. But okay, I think that I see. If I took, like, for instance, what I understand is that if you don't use monoticity, if I took an initial perturbation that was like a hat here, what would happen? Because this breaks the monoticity. But however, I claim that it would be the same thing. It would converge here, and then it would just translate the shock. If you numerically compute it, it works. However, if you use the monoticity, you can't prove it. But it's true, in fact, when you compute it. Does that answer?
Yeah, but if you have two bounds interacting before, far from the profile, so maybe these bounds are generating new shocks and so on. So I don't know.
Yeah, but they're traveling at the same speed. So, for instance, I have another representation. So maybe I can show this. I don't know if it's what you mean, but like I was.
Maybe I do.
No, not the right one.
In their case, they are no more traveling at the same speed.
This. So
Right.
something like this. You mean like you have a. But if I apply, they're just traveling at the same speed, so they don't really interact. They can't interact because they are really just are translated.
They are traveling at the same speed because they're the same size. If you take
really
different sides, they are
different.
working. They are traveling at different speeds, so I'm not sure.
Maybe.
Anyway, I mean,
okay.
it's not-
I see what you mean.
For example, to your theory.
I see what you mean. Okay, that's okay. I
For
understand.
the system, general system, not for the scalar case.
Okay.
Scalar case, I'm sure you're right.
No, but I can.
Okay, maybe other questions. So, there is no comment, so maybe we can stop here and we can continue the discussion privately. And anyway, thank you again
Thank you
for your talk.
Thank you very much.
Vediamo arrivederci.
Talk.